This is a step-by-step introductory level introduction into the fractional calculus, which generalize derivatives and integrals to non-integer order. The example we're going to work out in full detail will be this one. We are going to be taking the 1/2 derivative of x and arriving at 2 times the square root of x over pi. The theory of the fractional calculus begins with the same definition of derivative that we're introduced to in introductory calculus, namely that the derivative of f of x is equal to the limit as epsilon tends to 0 of f of x minus f of x minus epsilon divided by epsilon. The difference will be that the second derivative will be defined by a new iteration process. This gets mapped over here. And if you notice on this left side, we have f of x minus epsilon. And we're going to subtract off f of x minus epsilon minus f of x minus 2 epsilon. So what's happened is that we had here x minus 0 epsilon, x minus 1 epsilon. And over here we have a shift by 1 epsilon, x minus 1 epsilon, x minus 2 epsilon. When you work out the algebra, you obtain this result. If we iterate one more time, you'll begin to see a general pattern arising. Again, this becomes the left side over here. And we're going to subtract off this side, which is just the same as the previous side over there, except shifted by 1 epsilon. As you can see, here we have no epsilons taken away, 1 epsilon, and 2 epsilons. And here we have a shift, 1, 2, and 3 epsilons. When you clean it up, you obtain this. Iterating n times, you obtain this. Let's take the second derivative of x to the 4th. Here we go. Second derivative of x to the 4th. Here's the formula for it. The summation will happen from j equals 0 to j equals 2 in increments of 1. We have 1 over epsilon squared here, minus 1 raised to the jth power, our combinatorics here, and f of x minus j epsilon. Our function is x to the 4th. There it is right there. If you expand the summation out in full detail, you obtain this. It cleans up into this. Go ahead and expand the parentheses to the 4th power, and then subtract off everything that cancels. And we obtain this result right here. So that when we take the limit as epsilon tends to 0, we get 12x squared. Exactly the same result we would have obtained using the second derivative that we came to learn in calculus. And one thing you have to notice is that taking the second derivative of x to the 4th was not a local process. We had to evaluate the function at the extreme right, shifted over by 1 epsilon over to the left, and shifted over by 2 epsilon to the left. The derivative, as defined in the fractional calculus, is a non-local beast. The question to ask is, can we have fractional factorials? And the answer is indeed we can. If you consider this integral right here, we have a way to access n factorial. Solving for n factorial, we obtain that. And if you look at this, when n is 1/2, 2n times 1/2 plus 1 is an integer. In fact, anytime n is half integral, that quantity is an integer. And the same applies for the exponent of 2. If you're interested in seeing how we obtain this strange result up here, we recognize that the integral is a trig integral. When we do our substitutions and change our limits, we obtain this integral right here. When we have an even case, we obtain this symbol right here, a strange looking symbol. It's equal to this. When n is odd, the strange symbol is equal to this. After all of the simplifications, we obtain this, which is this. Evidently, we can have n being half integral. I've said half integral, but positive or negative. In this case, we don't have an issue with setting n equal to positive half integral numbers. We can get away with n is equal to negative 1/2 and still keep this to be 0. And 0 factorial is 1, and 2 to the 0 is still 1. In fact, we can have any negative fraction that we wish. The function that allows us to do this is the gamma function, and its connection to the factorial is this. So with the gamma function, n can take on fractional values that are positive or negative. So it turns out that the iteration process that we began with that led us to this formula generalizes to this formula with the use of gamma functions. We can sum to the absolute value of x minus x naught over epsilon. So one thing to notice about this symbol is that when n, the binomial coefficients vanish when j exceeds n. As epsilon tends to 0, the n values of f of x minus j epsilon with non-zero binomial coefficients converge on x. This lines up with the derivative that we were taught in introductory calculus. Those derivatives are local, and so are these, because of special reasons. We are still evaluating them non-locally. I'm going to define two operators that will show us the connection between the fractional calculus and the integral calculus. I'm going to let this operator, sigma sub epsilon, acting on f of x, be f of x minus epsilon. And I'm going to define this differential operator, d to the nth, as the limit as epsilon tends to 0, of 1 minus sigma sub epsilon over epsilon raised to the nth power times f of x. If we consider the first derivative, in this formalism, we recover the derivative that we were taught in introductory calculus. Here's where it gets interesting. What is the -1 derivative in this notation? The consequences show up right there. If you recall this result, this expansion, and if we let epsilon equal to x divided by n minus 1, this, which is this, becomes this expansion right there. If you collect the terms, you obtain this. That looks like an integral. In fact, it looks like the integral from negative x to 0 of f of x dx, or changing the limits of integration, it is the integral from 0 to x of f of x dx. So differentiating to order -1 is equivalent to integrating f of x from x naught, usually set to 0, to x. In the theory of the fractional calculus, integral is seen as the negative derivative of a function. At this point, it's worth remembering that when we were first taught integration, we understood it to be a non-local concept. You are evaluating the function along a partition. So let's get to that promised half derivative of x. For taking the half derivative of x, we're going to set m, or really mu, to 1/2 right there. Rewriting it this way, we get that. Expanding it in a series, we get that. We're going to set x naught to be 0. And we're going to differentiate by starting at x and then shifting over by 1 epsilon, by 2 epsilon, until we continue to do this so that we arrive at 3 epsilon away from 0, 2 epsilon away from 0, 1 epsilon away from 0, and finally 2, 0. Substituting into our formalism, we obtain this result. Plugging in the actual values, we get from here to here. Then you go up and look up gamma for 3/2 and gamma for 1/2 and -1/2. And when you do this, you arrive right here. The next bunch of steps are just algebraic collections. Here, 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 arriving at the penultimate step where we take the limit as epsilon tends to 0 and obtaining the promised result. The first time I ran into the fractional calculus was when I ran into this book at a bookstore. I had gone through a bachelor's degree in physics, a master's degree in mathematics, and a doctoral degree in physics, and years had passed by when I ran into this book. So it was quite a surprise to see this generalization of the calculus, which has lots of applications. The presentation you're seeing, however, was inspired by this website, which I encourage you to visit. It has a lot of history and is very well written.